Now we're going to explore how you would use a dimensionless solution to get real answers to specific engineering problems. So let's take a look at that. In order to move forward, we need to actually select a real velocity scale. So up until now for this problem, we have used u infinity as a velocity scale, but there is no real u infinity in this problem. Obviously, this is interior duct flow between two plates. There's no free stream velocity. So u infinity was just a placeholder for, as I said, when we derived the dimensionless equations, for just whatever characteristic velocity we think is appropriate for the problem. We already chose the characteristic length scale to be h, which was the gap between the plates. Now we're going to say, well, let's choose one of these u's that we could choose. Now the two that you could choose that would make any sense at all would be either the average flow velocity or the maximum flow velocity. Those are the two u scales that you could choose. And I think either of those would make sense. But we're going to choose the average flow velocity as our u scale. And the reason we're doing that is largely because it is the most accessible. And you're probably learning to get a sense for that in class, that you often can get the average flow velocity because you can measure a flow rate, either a mass flow rate using a scale over time, or a volumetric flow rate by using a volumetric measure over time. So those are usually the most accessible velocities to the experimentalist. So let's use that as our characteristic velocity scale. That means that the dimensionless velocity is now going to be defined as u divided by the average flow rate. That means the average dimensionless velocity, the big U tilde, is equal to U bar over U bar, which is simply equal to 1. So the average velocity flow rate in this formulation is simply 1. That turns this equation, where we determined last lecture that the average velocity in dimensionless terms was negative dimensionless g times the Reynolds number based on h divided by 12, that turns it into this formula. And we're going to talk more about this in a little while. But notice how simple this is. So in dimensionless terms, g times REH over 12 is simply equal to 1 with a negative sign. So that's a very simple formula, and that is typical of proper scaling, that things should start to look simple and clean. We're now going to use that also new scaling in our relationship for U tilde. So U tilde, the relationship for the velocity profile, we found that it was minus g REH over 8 times 1 minus 4 y tilde squared. But now we know that g REH is equal to just negative 12. So U tilde is going to be equal to negative 12 over 8 times 1 minus 4y tilde squared, right? Because that just comes from here. G REH is equal to negative 12. So we have negative negatives. So that becomes a positive. So that's going to be positive there. And we have that the U tilde is simply equal to 3/2 of 1 minus 4 y tilde squared. So that also an extremely clean result. So we have that if you want the velocity in dimensionless terms, it's simply 3/2 times 1 minus 4y dimensionless squared. So a very, very clean result. So these are our two big results in dimensionless terms. And as I said, if you're doing scales properly, this is the kind of thing you look for, where your solutions start to look very clean and neat. So notice how little is in here. It's just one dimensionless length scale, and that's it. Everything else is just numbers and constants. All right, so now we've got these solutions, and we want to remember exactly what this entails. So these two solutions are very clean and neat. I'll write them again here at the top of the paper. G tilde REH over 12 is equal to 1, and U tilde is equal to 3/2, 1 minus 4 y tilde squared. All right, that's fine. Now, how would we really use this? In order to use this, you need to remember all of the variables that are here, right? So we, of course, hopefully, by this point, you all really remember well what the Reynolds number is. But we chose as our velocity scale U bar. So average velocity would be the velocity used in that Reynolds number. U tilde, of course, we just said was U over U bar. That's the same statement. And G is dp dx, but it's times h over rho u bar squared. So these are the terms that you have to remember if you're going to try to use this to solve anything. So now I invite you to try to solve something. So let's take a look at an example problem. Let's find the average velocity if delta P is equal to 1.25 newtons per meter squared from inlet to outlet. That's going to be P in minus P out. And L is equal to 7 meters. And H is equal to 0.02 meters. And I want you to use the dimensionless technique, and the fluid is water. So start with these equations that you have here. All of it's right here, these equations, and use these equations to find the actual, with units, volume, the average flow rate given these dimensions. And the fluid is a water. And after you've done that, I want you to find the velocity, the actual velocity, at a particular y position, 0.005 meters up in the channel. Remember that the channel, the y-axis is in the middle, the x-axis is in the middle of the channel, so this would be halfway to the wall going upward. So it's 0.005 meters for that. So that's your assignment as an example problem. So why don't you take a little time and see if you can make any progress on that, and then click on the next lecture.